Good morning, everyone. Welcome to our first Telemetry and Big Data workshop. We are starting today with 4 longer sessions. I would like to invite Mauro Campanella, who is the initiator of the idea for this workshop and also chair of the program committee. To start presenting and announcing the content of this first session.
Thanks, Ivana, and welcome to everyone. I'm very glad to start this Telemetry and Big Data workshop. The idea started in the GÉANT project, but apparently is quite popular in the need of many. What is GÉANT? For the people who are not familiar with that, actually GÉANT has at least 3 main meanings, or 3 hats if you want. Is the GÉANT Association, the legal entity of all the European NRENs. The GÉANT Operational Network, which is the one who most of us probably are familiar with. In the pictures below, you can see the European footprint as it is now. It will be larger in fibers in 1 or 2 years from now, because there are 2 projects that are enlarging the footprint. And on the right hand side of the picture, you can see the global reach of GÉANT, making easy for European researchers and projects to reach the various other colleagues in the world. The third meaning of GÉANT is obviously the project itself. Actually, we have now 2 running projects, the GÉANT-4-3, which is a more general project directed to maintenance of the network development and research, and GÉANT-4-3N, who is mostly targeted to acquire more fibers in Europe. The vision, I will briefly go through that, is actually to allow all scientists in Europe, and I would say also education in Europe, to access all the infrastructures and the resources and the collaboration worldwide. As part of the Horizon 2020 Research and Innovation Program, Horizon 2020 will end this year. The new Horizon Europe program will be funded, and GÉANT will be part of that program too. 40 partners, including universities, 500 people contributing to the project. We estimate that just through GÉANT and the NRENs, the combination of these 2 networks reached about 50 million users around Europe. The project is started 1st of January 2019 and will proceed for 4 years. We are at halfway of the project. Why telemetry and big data? Well, the idea came from at least 3 different tasks in Work Package 6, which is some kind of an incubator at the same time as service development and production, network technology evolution, service evolutions, and monitoring and management. The idea is that we joined forces and started to understand how telemetry can benefit all these areas. The presentation today provide an overview of what we have been discussing and doing the last 2 years or 1.5 years in 3 main points: data plane programming and in-band telemetry, streaming telemetry, and how to use data plane programming for more elaborate algorithms in the data plane that may actually facilitate our work. Why telemetry? Well, telemetry is that we are moving to a higher speed, higher footprint networking, and I would also say much more populated by devices and persons, the networks themselves. So we are really scaling to a lot. Terabit is one common keyword now. The challenge is how to understand better what is happening from the production point of view, but also from the researcher's point of view. And then to understand that, we have to analyze the data what we will create and present that through a kind of service-oriented views. We need to provide a set of services to the various users. One is connectivity, but not only. So we need to control and debug, and both need that more in-time, real-time information. So we are not just managing larger networks, that's the other point. Our networks are more and more intertwined, I would say, with computing for various reasons. And the SDN approach is clearly towards adding more and more computing and software to our networks. I, on purpose, reported what the Wikipedia says about telemetry: in situ collection of measurements or other data in remote points and send them back to receiver equipment. That is exactly what we were used to do, but now we have more weapons in our arm to do that better, faster, and with more in-depth insight. And that was also due to the very fast improvement in the silicon. FPGA to Phenochip by Barefoot, even Juniper or others are already moving in that area. And at the same time, we have also programming environment to program these low-level devices. Details. The workshop today will be split in 4 main sessions, plus some coffee break and tea, and 2 discussions in 20 minutes chunks, one at the end of the morning, in which we may also have Mentimeter, and one at the end of the day. This is the program committee. Just a few reminders. The workshop will be recorded. Check your microphone that is muted, please, if not speaking. The presentations are all online on the wiki page of the workshop, and also the abstracts and the views. This is session 1 of today, and I will now proceed to the first talk about data plane programming and in-band telemetry. Just 1 second, I will have to switch screens. I will share the screen for the new presentation now. Data plane programming and in-band telemetry. Why that? We are a small group of people that started to understand what really means data plane programming and what in use case can present the in-band network telemetry. Why programming at the data plane? Essentially, indeed, software is becoming more and more widespread, but programming at the data plane is still a realm in which only the large providers producing the large equipment have had the possibility to do, and mostly based on their own choices on a fixed environment. I mean, they decide exactly what are the functions of their switches, routers from the beginning. They use it too. But data plane programming and the new equipment can actually permit us to innovate and change the behavior in the network in due course and very fast according to our needs. That has been permitted by the appearance of new silicon, virtual environment, of course, like in the BMV2, the FPGA, which is not exactly new silicon, but its capabilities have greatly been enhanced during the last years, and the use of a, let's say, high-level language, programming language that is very similar to C, but permits to program the chips themselves. When talking about data plane programming, two use cases actually came to our mind. One is the in-band network telemetry, gathering information in real time in the switches or in the application themselves, and DDoS detection, simple DDoS detections as a way to introduce algorithms. These reporting will be about DDoS will be done by other two talks, one this morning by Daniel Pernevich for GÉANT WP6 and also by Marinos Dimoulas. This is what it happened. We started with open user software, then SDN came out, and that actually permitted us as researchers and also as production environment to program them up to the network layer in a much more interesting and free way of doing what we need for our production environment. But now the appearance of these switches and the P4 language has permitted us to program down to the physical layer. And that has two advantages and two challenges. Actually manage all these layers, and at the same time, it ushered for us the possibility to access the big data of the users, but also of the network itself, because the network at that point can produce a very large amount of monitoring information. Just as an introduction, I'm sorry if it is known probably to most of you, but just to make the difference between streaming telemetry and in-band telemetry. Telemetry is the definition I've just mentioned before by the Wikipedia, is actually collect locally data and send that remotely for analysis. That is a profound difference in the way it is done in respect to an example SNMP, which you constantly ask the devices to send you data. Telemetry programs the device instead to send you data at the right time, so you receive information asynchronously from the devices. Streaming telemetry will be mostly described by Pavle very soon. In-band network telemetry exposes the information from the data plane directly, instead adding some information in the packets themselves. So it is instantaneous, it's line speed in principle, because the chips are fast enough. The information can be added by each node in the path, providing analysis of what the packet do in the network, their history, and also according to various content of the packet themselves, because you have full access to all the information in the headers at least. And if you have a data plane programming, then it is fine, because it's even better, because you can actually tweak what you want to access on a relatively fast way in all the devices. What we have done in GÉANT, we decided to build obviously a code, a P4 code for in-band telemetry. This is also provided by other sources, so we try to harmonize these with other sources. There are some standardization of in-band telemetry provided by ONF. But instead of but we wanted as soon as possible to test that in the real network, which means actually going in the production environment. Connect 3 labs, Poland, Czech Republic, and Italy FPK through GA, and use the production environment, sending some enriched flows and see what happens, because this is the best way to understand how to use int in a production environment. As soon as we started receiving data, we started understanding that the data are too many, if you want, or very large or big data, as usually we say. Even if you have only a few kilo packets per second, that is a lot of information anyway that you have to collect and present. So that was a key challenge also in int. We started with UDP flow, and the real goal is to prepare a tool that can be used by all the NOCs or the interested researchers to understand what happens in the network to their own packets, because one of the difference between streaming and streaming is usually averaged on a certain number of flows or all the flows that go through the switch. But with int, you can explicitly choose a specific flow or a specific packet and follow that in the network. This is what we did. This is the testbed. I want to be brief. Essentially, in PSNC has the collection and is the sender of the UDP flow collected by SESNet, and then all the information of int is sent back to PSNC for collection and presentation. It's not needed. You can do connection and presentation at every size. We just simplified and had one central point for collecting and presenting all the information. The red dots in this picture shows where the locations are. All these locations and all these traffic that I will show you goes through the production environment. We do not disturbate the production environment. Our flows are, for the time being, are kept at less than 100 megabits per second, so not to disturb the other official researchers. What are the steps? Well, it was first, obviously, to define what we wanted to measure, and we started with the usual timestamps, sequence numbers, to understand what our networks do to the packet. Do we lose packets? How is the timestamps? How is the delay variations, and so on. When you choose what you want to measure, then you have to code. Coding using P4 in the high-level silicon is non-trivial in the sense that you have no longer the freedom of a lot of virtual memory as in the usual computers. You have a fixed memory amount in the chip itself. You have a fixed amount of registers. You have, in particular, a fixed timing if you want to keep the line rate in those switches. So it's, I would say, tricky, interesting, and different from the normal programming. When you start from the, thanks, Ivan. When you start from coding, you start from the virtual environment provided, VMV2, and then you go to the normal environment. You collect the data. Collecting the data, you need to choose a database. Now we are capable of ingesting 100K packets on a single thread. Present, Grafana, and analyze. This is one of the key issues that I wanted also to highlight. We are not talking about technology. We are also as much as interested in the understanding of our networks. And this is, for me, is knowledge. We need to understand how to understand a network at 100 gig or at many, or at an average, which is not the 5 minutes of SNMP, is a few seconds. So everything is still perfect? No, not yet. Time synchronizations between sites and node clock stability. This is just to show you what we get. We had a 2 kilobits per second packet flow, which 2 kilobits per second means between packets you have half a millisecond, and this is the plot we devised. This is only few seconds. And then if you go over, this is 1 hour. This is our network, how our network behaves at the microseconds level. Next step, we want to test more functions. We are now just testing the sending and receiving in the packets. We want also to add intermediate nodes. So we have also the transit internet things. We want to enlarge topology. So if you're interested, please keep in contact with us. Other case, everything works not just in the wide area networks. It works on cloud or an LAN, because that can also help in debugging the complex environment in the virtual stacks. The nice thing is that we are devising a tool that can use DPDK, which is an accelerator for networking in a normal computer, I would say, that would allow us to use off-the-shelf hardware without the need to buy new silicon. Summary, I think that data plane programming is not exactly as the way of programming the network as we are using, but it's very useful because it actually permits us to understand much, much better what is happening. Int is a magnifying glass in that sense, especially if you need to debug very strange things. The raw data that you produce in just a few seconds is a very large amount, and you have to handle that in the right way. But that is, I would not say is a con, is a pro, is an advantage that provides you much enrichment. Please contact me for any new things. I hope I stayed in time. Back to you, Ivana.
Thank you very much, Mauro. So our next presenter is Pavle Vuletic. Pavle, would you like to share the screen? He will tell us about the streaming telemetry work that is done in work package 6, monitoring and management task.
Thank you, Ivana. I hope you can hear me well. Good morning, everybody. So my name is Pavle Vuletic, coming from the University of Belgrade and AMRES, partner in the GÉANT project, and I will try to tell you in 10 minutes what we did in one of our subtasks in work package 6, task 3, where I'm the task leader. So there is this strange name in the title called zero footprint monitoring, and I will try first to explain what we try to did in our task. So what is zero footprint monitoring? Zero footprint monitoring is monitoring without adding any additional device into a network POP. And you will see today a lot of presentations where people will propose different monitoring methods which require adding something into the network POP. But if the network is covering a wide geographical area, and if the NREN or the network operator is centralized, then it is not so easy to manage all these devices, and it is not always the best idea to add additional device to each and every network POP. So we wanted to see if it is possible to monitor performance, and when we say performance, we mean basically SLA parameters like delay, jitter, and loss. How can we do it without adding new devices in a network which is multi-vendor, which contains different devices from multiple sources and so on. So this is a zero footprint approach. It was not possible to be done a couple of years ago because different network vendors like Juniper or Cisco had proprietary protocols, and there was no standard protocol for monitoring this type of metrics in their software portfolios. What we saw as a trend is that monitoring probes became smaller and smaller, and people started to use something like Raspberry Pis or virtual machines. But even this means adding additional device to a POP. This means potentially having additional visits to a POP, and this is why we wanted to explore how can we monitor the network, monitor network performance and network services without adding any additional device. And also we wanted to see how we can monitor the whole path, the end-to-end segments, and separate network services. As I will show, we succeeded in this, and we were able to do this because the landscape has changed recently. So TWAMP implementation started to appear in the software portfolios of the biggest network vendors like Cisco and Juniper, although Cisco had a partial implementation of TWAMP with only responder. But on the other side, there is a possibility to install a virtual machine on top of a router, or to have a guest shell, which allows installing monitoring software on a router, and which means that you can actually do the measurement without adding any additional device. So we wanted to test, are these implementations interoperable, and also can this be used for detailed network performance monitoring? And of course, in the title of this presentation, you have streaming telemetry. We exported the results of the measurements using streaming telemetry. So we tested TWAMP in all different combinations between the two hosts, Linux machines, and the Internet to a persona implementation of TWAMP, between the host and the router, between the router and the router, which means also between two Junipers and Juniper and Cisco, and vice versa. We also tested virtual services on a router, which means virtual machine on a router, and all these measurements were successful, as I will show later in the presentation. Although all these implementations are interoperable, the metric set is not the same, and you can see here, for example, the Juniper and Linux has a slightly different set of metrics that you can get from TWAMP. Mainly the differences in the inter-arrivals that are added by Juniper machines. We tested our approach in this big testbed, which consists of various different devices. Those H boxes are hosts, Linux machines. VMXs are Juniper virtual routers, and XE is Cisco virtual CSR. And also you can see on the right-hand side of this slide something called UOC. This is Ubuntu on Cisco. This is not a separate machine, but this is a virtual machine which is installed on Cisco. And we tested the path between two different VMs, between H1 and H5. Also, as you can see, the testbed allows us to create various different topologies and paths between those two endpoints. So we also tested path changes, and we added latency and jitter between some of the segments, because what we wanted to see if with using this approach we can pinpoint to a faulty segment, to a segment between the two routers that has increased delay or increased jitter and so on. So we managed to test also all these scenarios. This slide will take me another 10 minutes to describe it, so I will not go into details. It basically shows on the lower three graphs show the end-to-end path, and you can see those added jitters and added latency and changes in the path. And on the upper part of the slide, you can see per span, the parameters per each span on the path between the two endpoints. There is a document, and I will tell you at the end of this presentation, which gives all the details of all the experiments that we did in much more details. But basically, the conclusion here is that all the combinations of TWAMP implementations in network elements and hosts are interoperable and work flawlessly. And now we are coming to the part which has this streaming telemetry in the title. So we wanted to test how streaming telemetry operates in this environment, and we wanted to use streaming telemetry with the two different vendors that we had. Why? Because there are big promises that it allows faster retrieving data from the network elements, that it allows more reliable, that it is more reliable, and it is, because it uses TCP unlike SNMP, that it is more secure because it uses TLS, and definitely this is more secure than some older versions of SNMP. It is expected to have a smaller processing requirements in comparison to SNMP, and also if you are using programmable data planes, then maybe you can define your own data that can be streamed using streaming telemetry. And all this is something that sounds promising, but unfortunately streaming telemetry is not yet, does not yet have the state of maturity that SNMP has. So the implementations are slightly different. So you can see here that the transport methods are different in Juniper's and Cisco's. Juniper has UDP and gRPC, while Cisco is using NetConf, gRPC, and GNMI. And there are different data models that are being used by these two vendors. But still, this is very similar, and we were able to relatively easily do all the to stream all the data from our network elements toward our monitoring collector. We used both dial-in and dial-out streaming telemetry from the routers. Dial-in is something that is very similar to SNMP, where the collector is polling the network element and asks for a specific variable to be sent to the collector, while dial-out is something that is unique to streaming telemetry. It is not in a way that, I mean, SNMP also has a sort of dial-out with the SNMP traps, but SNMP traps are constrained to only specific set of voids where you can define that upon some change or upon some event, the message is sent to the collector. But in the case of streaming telemetry, it is possible to configure that all the variables are sent either periodically or on some event to the collector. And you can find in the document that I mentioned, you will find a lot of examples of various configurations for both types of routers. For dial-out, which sends the data from the router without being asked, and also for dial-in configurations, as you can see on this slide. We used, I think...
One more minute, Pavle.
Okay, thanks. We used, I think, the most common set of tools for exporting this data from the routers, which means Telegraph, InfluxDB, and Grafana. And you saw Grafana graphs a couple of slides ago. Also in the document, you will find some examples how you can configure Telegraph to receive the data from both types of routers. So conclusions: all the TVAMP session combinations gave very similar results, show reliability. Our network was not heavily loaded, but even if it was heavily loaded, I don't think that we could make some conclusions how the real network would operate, because our network was completely virtual one, built on virtual machines and virtual routers. Monitoring network services using standard-based protocols and no additional hardware is possible, and you can also get the information about the spans, the specific spans within the network. Streaming the results from both router platforms was without any issues. It was very stable and worked for a long time without any issues. How the whole process is not always straightforward. So setting up some of the elements like virtual service on the Cisco router or finding XPaths is not always trivial. So this is why we decided to create this document, and this document is finished, but it waits for someone who speaks English a little bit better than us who wrote it to take the last look, and this will become the official cookbook document for zero footprint monitoring, where you will find additional information about TVAMP interoperability, virtual services on routers, and streaming telemetry. If you would like to get this document before it is officially being published by GÉANT, please drop me an email. I will send the draft version, and please don't complain if you find some grammatical errors in it. So thank you very much.
Thank you, Paul. Apologies in advance to all the presenters. We have very, very full schedule and we really have to stick to the time. So our next presenter is Rick. Rick, if please share your slides. As you can see that we at the moment do not have much time for questions. Please put any questions in the chat. If we finish earlier, then we will address them in the air, let's say. Rick, please.
Thank you, Pavle. Because Pavle explained so well and very quickly a lot of the tenets of what we're trying to accomplish in this workshop, this will make my presentation a little bit shorter. So thank you, Pavle. So historically, as was mentioned, there were a lot of methodologies that lasted a long time, but they just don't scale in this new era of terabit networking. All the old things that had been done in the past, I mean, we squeezed them as best we could in order to make sure that we could still monitor the network. But as we all know, they just really weren't sufficient. And here's why. I mean, typically we can't pull any faster than 5 minutes. You can't pull the data fast enough from the devices because routers are meant to route, and SNMP is a secondary function in the grand scheme of things of what they're trying to accomplish. But without monitoring your network, you don't really know if they're doing their primary function properly. So you've got this kind of catch-22 of you really want to monitor things closely, but if you monitor too heavily, you end up interrupting the routing because you've made the routing engine so busy with answering your SNMP queries that it can't actually route packets, or the router protects itself in its primary function and it starts to ignore your SNMP queries because it needs to get on with routing packets. So with that, you get a lot of smoothing, you miss all the microbursts, and every tool that you add on, that needs to add additional load to the routers themselves in beating up the routing engine. And it ended up in GÉANT that we needed to have multiple servers in place for just a single tool in order to get the complete polling cycle sorted within that 5-minute cycle. And to be honest, that added a lot of complexity and a lot of fragility to the tool overall. And it's just not a satisfying experience in a grand scheme of things. And as Pavle very well covered in his presentation about security and transport. So, as was mentioned, there are a bunch of things that need to be done. First of all, for us was upgrading. We are currently in the midst of upgrading from GNOS 17.4, which has some elementary streaming telemetry support in it. But the move to 18.4, it should give us the full suite of streaming telemetry. That has been fraught with difficulties. Anybody who's worked with Juniper recently, you know that their QA has been, well, suspect for a few years, to be polite. And with that, even with all the lab testing in the world, and we do a lot of lab testing prior to recommending a release for production, we end up finding zero-day bugs. And part of that is because of how we operate. Being a collaborative network, we turn on all kinds of features that no sensible commercial service provider would turn on because you just can't monetize it. So with that, we're special in the NREN communities. So we've had several false starts. We are about 2/3 of the way through the GÉANT estate as far as upgrades. And if everything goes according to the OC schedule, we should be finished just around the middle of December before the change freeze comes in. So with that, it means we can move on and start looking at streaming telemetry in anger. We've been doing this in the lab for a while. We've been exporting stream telemetry data to our software development folks who have written a parser to consume this data. And as Pavle mentioned, we're using the same tools that everybody else is using because, well, it works. So why reinvent the wheel? Using Influx and Grafana. And when we start going at scale, as Pavle mentioned, the use of Telegraph to decode the protobuf streams. Juniper had initially backed a tool called OpenNTI. They have abandoned that in the last year or so, not openly, but by omission, shall we say. They had been backing updates to that tool, but then just kind of stopped once they had their own tool, HealthBot, that was made available. And the main plus from them on that side of things is it integrates directly with their PCE controller, Northstar. Just slots in and is simple from their perspective. In some of the newer versions of GNOS, they will be adding additional functionalities that, again, once Pavle has covered in great detail. And thanks, Pavle. You've really made my my presentation a lot simpler. And those services that that Pavle mentioned, the GNMI and gRPC later on, that is more specific to the MPC 10, which is Juniper's 400 gig line card for the MX series. And we've already actually put in a purchase order to get these, and we will be upgrading the Western Ring to 2x400, probably Q1, Q2 in 2021. And with that, we want to be able to support all of the streaming telemetry options that are available to us to see what works best for GÉANT, because we haven't determined what's going to be best when we start doing these monitorings at scale. And with that, like I said, mine was going to be short because Pavle so well explained all the rest of the stuff. So thank you very much.
Excellent. Thank you very much, Rick. Let's now continue with our last presentation for this morning, with this morning session before the first break. So it's Damian Parnievich from PSNC, use of sketches in DPP for DDoS and monitoring. And then if we will have some time, then maybe we can address some of the questions.
Okay, hello everybody. My name is Damian Parnievich. I'm working as a network researcher at PSNC. I'm also part of the GÉANT data plane programmability working group. And in this group, we are also investigating the usage of the programmable platforms for the improved network visibility. In this presentation, I will try to give you a very short overview of benefits and problems we have encountered in our experiment with this topic and present, let's say, result of the usage of the on-switch analytics. Okay, I have some problem with switching the slides. I don't know what's happening. During this workshop, we already have discussing streaming telemetry and inbound network telemetry. Both methods provide a lot of useful information, but they are not so scalable. So observing too much at once can overload network monitoring infrastructure. So, so this is the problem, and there is a third option which I would like to talk about, especially if someone wants a scalable monitoring system giving fine-grained picture across the whole device. So on-switch analytics, these are algorithms working on data plane level of the switch. This kind of analytics is composed of a set of configurable and purpose-targeted algorithms calculating statistics, histograms, and similar things for every packet entering the switch. Such on-switch analytics produce small output, which can be easily exported from the device. This data plane real-time on-switch analytics is possible with the use of sketch algorithms. So what are the sketch algorithms? Sketch algorithms are stochastic algorithms, mostly based on very fast hash operation done for every incoming data. In our case, it is incoming network packets to the switch. Sketches use fixed small size memory, which is important because of the limited memory availability in the network devices. Sketched algorithms were invented more or less 15 years ago for the big data databases, and from this environment come to the networking. In programmable switches, sketch structures can be inserted in any place of packet processing pipeline. The good thing is that sketches are very fast because of this hash operation and can handle all packets from all switch ports. This way gather statistics coming from any set of frame fields or metadata produced by other logic element in the switch. As example of such data plane level analytics, we have been working on the DDoS detection solution for the P4 switches. We implemented a set of sketch-based algorithms allowing for the DDoS detection and very fast identification of destination IPs under the DDoS attack. The first goal was that the attack could be mitigated immediately on the switch, so the target and user could not be aware of incoming DDoS attack. However, decision about blocking could be also left for the network controller. Additionally, to DDoS detection, we implemented a set of sketch-based algorithm giving a network controller or a network administrator more information about ongoing DDoS attack. We identified useful characteristics of traffic ongoing to the target IP, the target attack by the DDoS, which can help to decide which traffic needs to be blocked. These helpful characteristics are most frequent IP source subnets in the attack, most frequent used source and destination ports, TCP or UDP ports, most frequent IP protocols, and total traffic volume towards a target IP address. Those characteristics are constantly monitored by sketches, and outputs of these sketches is provided to the network controller. Here are examples of internal structure of this algorithm. For this algorithm, we have used P4 implementation of different types of sketch structure, like count means sketch for IP frequency estimation, Bloom filter for header value membership check. I don't want to go into details of this algorithm. I would like only point to memory requirements. In some, all use sketches require about 800 kilobytes of chip memory. These are also tests performed by my colleague from FBK, which also they have been developing this algorithm, and they have used KDE tracet, which were mixed with simulated DDoS traffic. They performed DDoS detection tests with 100% accuracy. Additionally, there were some performance tests. 10G traffic was generated using the iPerf tool and sent through these sketches. Actually, it was not always 10G, because in some cases, the testing server was not able to generate the required number of small size packets. Okay, so this is the limitation of our, let's say, testing environment. However, main finding of the performance tests was that no traffic degradation was observed on the switch, both in regards to traffic volume and packet loss. There is also no noticeable increase of packet processing time. The use of sketches has some problems. So not only benefits, but some problems. First of all, sketches require that their parameters are configured properly in order to produce good estimation result. So we must first plan and predict what, let's say, network traffic would be processed, and then properly estimate the size of the sketches and other, let's say, parameters. Additionally, each sketch is entity gathering one particular traffic statistics. If more frequent statistic is required, then more sketches must be deployed in the data plane. However, more sketches means more kilobytes of switch memory required. So we must be aware that there are not so many resources, for example, on the Tofino chipset, and there is a limited number of pipeline stages. These stages could be occupied mostly with standard switching functionality, and it can be hard to add many different sketches. This is especially in current available Tofino chipsets. So we hope that in the future it will become less limiting with next Tofino versions. The last thing is that some more complex sketches cannot be implemented. Lack of arithmetic operations such as division or logarithmic makes sketch implementation much more difficult. But from our experience, with some, let's say, creativity, we can solve some problems. Here's another example of, let's say, this kind of the on data plane analytics. It is a hash-based operation performed on the switch, also on data plane level. Currently, this is just an idea which is planned to be implemented in the future in our activity. We would like to implement in P4 a reduction of the number of in-band telemetry reports that are sent to the int controller. We would like to use the fact that most int reports are mostly the same. And if we only could compare the following int headers at the int sync, so the int node which sent int reports, we could achieve a great reduction in number of generated reports. Some int fields, in-band telemetry fields like switch ID or ingress-egress ports must be exactly the same, whereas other fields contain continuous, frequently changing values. Such fields are hop latency or queue occupancy. In this case, in the case of these fields, less significant bits are not so important, and we could skip them during the comparison. We can think of this as a binary equivalent of threshold mechanism. Int headers also contain timestamps, which couldn't be compared this way. For timestamps, we could calculate some derivative values that can be more easily compared during the time. For example, we can calculate latency or interpacket time gaps and then apply binary threshold mechanism over it. At the end, we must combine all results and perform a hash function to get 32-bit integer value. This integer value can be compared very easily with a hash result of the previous int node metadata. So int metadata coming from the previous with the previous packet of the flow. If you would try to compare each int field one by one, then this will require a lot of arithmetic operation within the network chips. It will be probably too much to be effective, and hash operation seems to be much better approach to compare int metadata. We hope this kind of data plane analysis applied to the in-band telemetry will enable more scalability for this technology, especially for example, for 100 GA links. Okay, coming to the conclusion. In the conclusion of this presentation, I can say that thanks to the data plane programming, we have more options to enrich our monitoring toolset. I must emphasize that each monitoring approach has strong and weak sides. But there is no silver bullet which will solve all our problems with more visibility. We must identify which information is important and get the right tool. So data plane analytics is a new kind of tool currently available together with programmable switches. This analytics is good at generating global and high scalable statistics. We can use this approach to fastly detect outliers or react in the near real time. We can use it to complement other telemetry solutions, and that is very important. That data plane analytics greatly reduce requirements on big data infrastructure. Okay. Okay, that's all. Thank you.
Thank you very much, Damian. We have one question from Lars on the chat. Lars, do you want to ask it yourself?
Yeah, so it was mostly a comment, really, that it just is great stuff, right? But it looks complicated, and when things are this complicated, I always worry that it's another source of something you can overload to cause a denial of service attack, right? You have to make sure that all this code you run, the analytics on the switches, is bounded.
Yes, so for sure, if we, let's say, implementing some online analytics, some algorithms, put it in P4 in the switch, we must firstly test it very good. If, for example, it don't bring an additional latency or make packet losses. But let's say there are, okay, we currently use quite simple sketch algorithms. So it is mostly it is a set of hash operations, and our let's say results show that this it doesn't affect the performance of the switch. Let's say the only problem is the pipeline stages limitation and let's say memory requirements or coming through this using many sketch algorithms at once.
Thank you, Damian. We have a few more minutes. Are there any other questions for any other of our presenters? You can either raise your hand or unmute yourself and ask the question.
I just wondered, to the last speaker, do the pipelines to do the monitoring or the telemetry, I should say, add to the transit delay of a packet through the switch? Sorry if you said that at the beginning.
Okay, we can also, let's say, in the okay, in this idea, we making a hash from certain fields from the int metadata, and for sure we can add to this hash also information about the latency on the switch. Because it is this continuous value, but we must apply this the binary threshold mechanism on it. So we must only get the most important bits and let's say skip very small changes of this delay on the switch.